ride, right? Times derivative of h cubed. 3h squared times dh dt. That's right, but we know dh dt. And we know h at the moment in time, don't we? And so we're there. Oh, no, wait, hold on. No, we don't know dh dt. We want dh dt. We know dv dt. Sorry. Got that backwards. It's all right. So what is dv dt? 2 pi equals over here, nothing cleans up there, equals, let's see, 9/16 pi times what was h? 3, right? So 3 squared is 9. Okay, I already brought that 3 out, sorry.
Oh, yeah, okay, sorry.
So 9 again, and then dh dt. So I had taken this 3 and brought it out here to create this, and then I squared the h, and h was 3, so it popped another 9 out there. This all right? Divide pi on both sides. So you'll have what? 2 equals 81/16 dh dt. And now just flip and multiply both sides. What do you get? 32 over 81? So 32 over 81 equals dh dt. And if you want that as a decimal, you can get an approximate answer. It's approximately 0.395. What per what? Inches per second. So at exactly the moment that the water height was 1 inch from the top, the rate at which the water was coming up was 3.95 inches per second. 0.395. So almost half an inch a second is how fast it was coming up. I was thinking about an application of this one. Maybe not as relevant, maybe so, I don't know. You tell me what you think. But simple example would be like if you had like a dam that was holding back water, right? You know, here's your water behind the dam, and it's going to come up over the spillway, right? And you've got rain, there's water coming in. Then if you have some way to approximate, you know, with the rainfall, how much water is coming into this reservoir, then depending on the shape of the reservoir, you could actually determine the rate at which it's coming up. And at the instant when it hits in the spillover, like how fast is it coming up at that moment, and then you could determine what the volume would be coming out the other side, and then how many people should evacuate downstream, that sort of thing. I mean, like, you could figure out things that way, and might be useful, you know, at some point with someone.
Pretty cool.
I mean, a cone, I mean, you're never sitting there feeling, man, I'm thirsty, and you're like, I'm wondering how fast it's coming. I mean, that's not the point of this, right? Also, I'll point out that if you have something like, I want to go back to this right here, right? Just this. This was the derivative before we plugged anything in, right? We took the derivative. Just want to clean this up a little bit. dv dt equals, let's see, 9/16 pi h squared times dh dt. All right, that's this simplified without me plugging in the instant and time, right? We wanted to solve for this, right? I'm going to solve for that without plugging anything in. So you tell me if you agree with this. dv dt, I'll try and make this as simple as possible, over 9/16 pi times h squared equals dh dt. You agree? Okay. Now, this is the height of the water, the rate at which the height's coming up, right? This is the rate. Over here, I have some other relationships. If the volume coming in is constant, then the higher I am, right? The higher the water is, the bigger this number is, the smaller this ratio is. Do you agree with that? If this number is fixed, and I let h get bigger, the bottom gets bigger, the ratio gets smaller, which means that the height should become slower. The change in height should be slower, shouldn't it? But if I make h smaller, the fraction becomes, this part becomes smaller, which means the ratio gets bigger. So the smaller the height, the faster the rate. The larger the height, the smaller the rate, which matches up with the picture, right? In the beginning, it's coming up very fast. And then as time goes on, as height gets bigger, this ratio gets smaller, so the change in height slows down. On the other hand, let's say that you had a situation where well, that wouldn't work out so much. If this was not constant, right? Then if this was getting bigger and the height was staying the same, then this would have to get bigger. It's like there's an equality to it. If this side gets bigger, to maintain equality, this side must get bigger. If this gets smaller, this side must get smaller. The only way to make this side smaller for us is to change the height, because this is stuck. Okay, I just want you to see that you have something very powerful in this, because you have a real connection between all the variables in the problem and how the relationship between their, the rates at which they're changing, you know, how it's related. How the rates are related. How the related rates work. Wait, what's the section called? Related rates. Okay. Yeah, this is all about relationships between rates. That's what I'm trying to get you to see. When we plug numbers in, we get specific answers. But the whole topic is about how do you take an equation, differentiate it, and create this relationship between the rates of change. All right.
Most engineers use like simple designs.
I mean, I'm sure there's some related rates things in there. You know, I mean, they use a lot of different things. It's not just one. Depends on what they're trying to do. But you can do a lot more with calculus than you can do without. That's for sure. All right, this is a hard problem right here. It's a runner running around a track and a person sitting there watching them, like stalker style, right? There's someone running around a circular track and person's watching them, and we want to know at a certain point on this track how fast the distance between them is changing.
It's like car pistons you're telling us.
What's that?
It's like car pistons you're telling us.
You could almost look at this as like a car piston problem, but they're doing a runner and a track, right?
You just cut circle in half and like do.
You could, yes, you could do that, and just change the direction of the runner if you want. But when we show the construction of this, and I wish I didn't have the construction because it's going to give it away. Should I show it? I think you've probably already seen it. Read through the problem real quick. A sprinter runs around a circular track which has a radius of 50 meters. She runs at a constant rate of 7 meters per second. Her friend, see it's a friend, is standing at a point 100 meters from the center of the track. How fast is the distance between the two changing when they are exactly 120 meters apart? So here's the construction. Connect the two with the straight line, right? That's from here to here. And then I'll press play here. And let me speed it up, and maybe we can look at it as the piston problem. A little bit. The only difference between this is the piston doesn't really work like this. This part's the part that's moving, right? But it's similar. You know, there's still a lot of geometry happening here, right? Slow down. She's running way too fast. All right, so there she goes. She's running around like that. So the geometry of this I've given away because there are certain things in the problem that are always the same, right? How big is the track? It's 50 meters, right? So the distance between the center and the runner is always 50. And the person is standing 100 meters from the center of the track. So this distance is always the same. The only thing that's changing is what? The distance between them, right? I mean, that's what we're looking for, right? At a specific instant in time. If you have two sides of a triangle, can you solve for the third? If it's a right triangle, you can. But this is only a right triangle twice in our picture, isn't it? Is there any other way to solve for a triangle if you have three sides? I mean, if you have two sides? Law of cosines. But that requires you have an angle. You have to have the angle between the two sides you know.
Could you use like an opposite triangle? Like if it were to stop right there, you have another triangle on the opposite side of the 180?
Like make a rectangle?
Oh, yeah,
Yeah.
the angle one.
Where?
There, like you have a triangle there.
This triangle here?
Yeah, and then you have a triangle there.
Yeah. Let me try and sketch this. We might be able to get something like that, but we want to try this as efficiently as possible. Let me see if I can create the. I don't even know. I can just show. I'm basically going to. It's going to come down to me showing you how to do this, right? But trying to do it in a way that's most efficient, right? Because there are multiple ways to get this problem, but you can also get very lost in the geometry of this problem, trying a bunch of different things. In my general picture, (150), and I'll call this x. We want to know, or x is the distance between the two, right? It's my general picture. How about the instant in time? Actually, it's 120, isn't it?
Yeah.
That's my instant in time picture. What's my given? What's my
You would
what
do
I-
that comment.
what am I given?
Or do you-
You're given 7 meters per second.
7 meters per second. What is that in my picture?
DST.
It's d what? She's going like this, right? Around the track? 7 meters per second is her speed around the track. I don't see a variable on our picture that's going to help us get, like, do you see a variable that represents her speed? You see the challenge here? I mean, it's not x. She is not moving, and x is not changing at the same rate the whole time. So I'm just going to put here 7 meters per second equals d, shoot, I have no idea, d something dt, right? I don't even know how to label it right now because it's weird, right? What do I want? That I can label, right? dx dt? Okay. When do I want that? When x is 120. Understand the setup so far? I need to connect what two variables? I don't even know what two variables, you see? I don't even know what two variables to connect because I don't even know what this is. But I was thinking that maybe we could do this using law of cosines. Because I knew two sides of a triangle, right? Law of cosines. But law of cosines would require that I know what things. So, does anyone remember law of cosines? Off the top of their head?
Cosine
Cosine capital A equals
A squared
A squared.
plus B.
Uh-oh. It's all right. It's okay if you don't remember it, but you got to know where to go to get it. Is it on your formula sheets?
This.
What reference page is it on?
Should be on 2. Yeah. So
You were close.
cosine A. Well, it's backwards on here. It has A squared equals B squared plus C squared minus 2BC cosine A.
Okay, so it's solved for
A squared.
A squared. Okay, so give it to me the way it appears on your formula, because that's the one y'all will always,
A squared
okay?
equals B squared plus C squared minus 2BC cosine A.
Okay, I thought that's the one you were trying to give me. I thought that was the one you were trying to give me.
Just trying to do it backwards.
Okay, you can solve that for cosine, and you can get a different formula. So from pre-cal, there's different versions of the law of cosines depending on what you were given. Like if you're given 3 sides, you actually use the one where it's solved for cosine A. If you're given 2 sides and an angle, you use this. That's the law of cosines, which means that you have to have 2 sides, B and C, which we could label this one B. Let's label this one, let's say C. And then you have to know the angle. That would make this side A, wouldn't it? Like if this is little b and little c, this would be little a. And this angle right here would be big A. Right? I'm not sure if y'all are following me on this or not. No?
We can find cosine A by using this formula. We can find the value of cosine because we know A, B, C.
I'm just concerned that the x and the x is going to mess people up in here.
No, X is A.
X is A, that's what I mean, that x is A. Should I leave it as x is equal to A, or should I change the formula up there and replace all my, like replace this? You want me to change that right there to x squared, or you want to change that to A? Change this to A?
Yeah.
Okay, this is little a, but that changes this over here to dA. I think I can follow it, obviously. You know, like I'm putting it up here, but I want to make sure you're following it, so I don't want to confuse the variables in here for you. That makes the most sense to you?
Would it be okay to just put X equals A on the general formula?
Yes.
And then just leave the rest the way it was?
Yes, but now you've got to just make sure you carry that the rest of the way and just be careful with it, that's all. So A is 120 here. Okay, so again, there's something very subtle here. I mean, I'm going to want to differentiate this formula, maybe, right? I'm going to need to differentiate this formula because it's the one that seems the closest. I'll get a dA dt out of this, won't I? Which will be what I want, right? So I'm happy with that. B and C, these are constants, aren't they? The whole time, which is why we chose this formula. B and C are always, so that's a constant, that's a constant. This is a constant sitting in front of cosine of A. So if I'm going to use that formula, what other d something dt am I going to need to have?
D theta? Or
D,
capital A?
d capital A dt, right? I'm going to need, if I'm going to use that formula, I'm going to need d capital A dt to be my given. So my question to you is, do you know that? You don't know it directly?
No, but you can figure it out.
Can you? Yeah, look, if this girl is running at 7 meters per second, right? Running around 7 meters per second. It's going to take her a certain amount of time to go around the track once. So if it takes her, let's say it takes her 10 seconds. It's not, but let's say it takes her 10 seconds. Then hasn't she done a full rotation in 10 seconds? Hasn't she gone 2 pi in 10 seconds? And isn't that a rate of change in angle per unit time? So we just need to figure out how long it takes her to go around the track. How long does it take her to go around the track? Well, don't we need to know how long the track is? Don't we need to know its circumference? Do we know the radius? Can we get the circumference? Yes. So this is all about, we're going to figure out what dA dt is, d capital A dt is, by using her linear speed and converting her linear speed into an angular speed. This is pre-cal. So let me try and get her linear speed to an angular speed. Her linear speed, there's formulas for it too. In pre-cal there was formulas of how you go from linear speed to angular speed and all that. But to me, it's always made more sense just geometrically. If you cut this track open and lay it out, it's a straight track, right? How long is the track? It's the circumference, which is 2 pi r, which for us is 2 pi times the radius. What's the radius of the track? 50 meters. So it's 100 pi meters, right? That's how long the track is. That's the length of the track. How fast does she run? 7 meters per second. So how long does it take her to run that distance? The time it takes her should be the distance over the rate. Shouldn't it? So the time, what's her distance? It's 100 pi. The rate that she's running is 7. What is it? 44.
44.85 seconds.
Yeah, I'm just wondering if we should we go decimals now?
Or
I'm not sure. I don't want to go decimals yet. We're going to get too much rounding error. I'm not real comfortable with that at this point. Let's just say that's the time, 100 pi over 7. All right? That's how long it takes her to go around. So what is her angular speed then? Well, what's the angle she goes through in one lap? 360, but we need to do it in terms of 2 pi. So she goes and she does 2 pi turns, right, angle-wise. She does a 2 pi rotation in that much time. So her angular speed is 2 pi divided by that. That's her angular speed. So this is the distance she traveled. This is how long it took her. So her angular speed is equal to the angle, right, the rotation in radians divided by the time. So it was I'm going to put the answer right here. It was 2 pi divided by 100 pi over 7. And some good things happen here, right? You get some pi's to cancel. 14 over 100, which reduces to be 7/50ths. 7/50ths what? A is a measurement of an angle. Radians per time measurement in seconds. Okay. I hope that all made sense. We have her angular speed, dA dt, It's always the same because she's running at a constant speed around the track. So that's how fast her angle is changing. It's changing at 7/50ths radians every second. Right? And then we want to know how fast the distance is changing. We have a relationship between the two. Here's the formula. You replace A, B, C, or you replace B and C with your constants. I want you to take that the rest of the way on your own. I mean, just all you have to do is do your derivative, plug things in, solve for d little a dt. You will have a little bit of an issue because you are going to need to figure out at some point what capital A is. But that'll be the instant in time picture. So how about we make this a take-home quiz to finish off, and you can turn it in next class.
So you wouldn't have to derive b squared or c squared, would you? Because you know those quantities?
I'm not going to answer that. You either do or you don't. And I want to see if you know if you have to.
See, we have to figure out the angle.
Hmm?
That would
No, this is not the angle. This is the change in angle.
be. Okay.
So remember, you've got two pictures, right? In this picture, A is changing. How much is it changing by? 7/50ths radians per second. It's changing. In the instant in time picture, isn't this length 120? Which means that angle is fixed. You still have to figure out what that angle is, because when you do your derivative, you are going to get the derivative of cosine in here. You're going to have sine of A, and you're going to need to know what that is. So on a new sheet of paper, start the whole problem over, put your name on it, see if you can work through it from front to back, and get an answer. And you can round decimals, that's fine. Your answer should be in meters per second, because it's going to be the A is a measurement of distance over time. Sound fair? Okay. We've got about 10, 12 minutes. I've shown you some examples, but there are plenty of other examples in the book that have nothing to do with any of this and have completely different geometry. And I kind of warned you about this from the very beginning. There's no way I could show you enough problems to truly give you a feel for related rates. They're inherently troublesome because of the geometry involved. And it's normal to feel intimidated by them and kind of overwhelmed by them. But you have to try. You have to keep working at it and do what you can. Okay? I can't commit any more time to it. I think about a day. We've done about a full day on that. I don't think we can do any more. But I do want to introduce the next topic in the next 10 minutes because it's going to go pretty quick. Very quick, in fact. And I think you'll like it. It'll be refreshing compared to this. We have avoided, up to this point, when we were doing derivatives, we have avoided messing around with exponential and logarithmic functions, haven't we? I mean, we haven't even touched them, have we? And that's just the way the book is laid out, the way a lot of the calculus classes work, is that they save this until we've done all the rules, right? We've done all the power rule, product rule, quotient rule, chain rule. We've seen implicit differentiation. We've done some related rates now. But we're going to go and talk about a few functions that we had in college algebra that we haven't talked about their derivatives yet. And the two functions that we're going to look at are the natural exponential function this is 3.1 and 3.2 and 3.3. That's where we're headed. But no, wait, sorry. 3.1, 3.2, 3.3. 3.1 and 3.2 are a review from college algebra. It's just, hey, what's an exponential function? What's a logarithmic function? If you need to go back and review those. I'm here to talk about the calculus of these now. All right? So we have the natural exponential function, and then we have what we called the natural log.
So to clarify, we're on 3.3.
We're on 3.1, 3.2, 3.3. I'm blending it all together.
Okay.
Yeah, because I need to talk a little bit about them. Like, you need to remember what they look like and everything else, but I'm not going to spend an entire class on reminding you what the exponential functions, how they behave, and all the properties. Just going to point out that we had them. An exponential function, the natural exponential function is the function f of x equals e to the x. And it looked like this. Do you remember that? It was exponential growth. It had a horizontal asymptote of the y-axis. Ooh, that doesn't look flat. Had a horizontal asymptote like that out the left side, but on the right side it grew, right? We'll get to the natural log next class. But those are the two things we're going to talk about. All right. So now that we're calculus students, let me ask you this. What's the limit as x approaches negative infinity of e to the x? 0. So it's saying, what does this function do as you go out this way? It goes to 0, doesn't it? What is the limit as x goes to positive infinity of e to the x? Infinity, right? We can see it from the picture. As we go to the right, the function takes off to infinity. What we didn't talk about yet, though, is what's the derivative of this? Right? What's the slope of the tangent line? If I say, come out here, pick some point out here, 2, and then come up here and find the slope of the tangent line, you would need to be able to take the derivative of e to the x. So how do you take the derivative of e to the x? What is the derivative of e to the x? It seems natural to want to know that, right? Does everyone remember e is just a number? It's like 2.718, something like that. Yes? And so if I change this instead of e to the x, if it was 2 to the x, it would still kind of look like this, right? It would just have a different sort of slope pitch to the growth. Like I could make this 10 to the x. E to the x is just a very special choice of the base, isn't it? Very special choice, and no one ever tells you why it's so special. Right? They just tell you it's a really special number, right? That's what they tell you. Well, here's why it's special. The derivative of e to the x is actually itself.
Why?
Well, yeah, why? So let's first understand what this is saying. If I take a function, I'm going to try and contrast this with something below it. If I take the function f of x equals x squared, what's the derivative of that? 2x. So if I graph x squared, it looks like this. Well, I missed the origin completely there. All right, there we go. So that's x squared, right? If I come out to the value of 1 and I go up here and I say, what's the slope of that tangent line? Everyone here is going to go, the slope of that tangent line is 2, because you plugged 1 into the derivative. And if I come out here to 2 and I say, all right, everyone come up here, and what's the slope of the tangent line? Everyone's going to go 4. And if I go out to 3 and I say, what's the slope of the tangent line there? Everyone says 6, right? That's how this works. According to this, if I come out to if I look at e to the x and I come out to 2 and I say, everyone come in, plug in 2, what's the slope of the tangent line? Everyone's going to say e to the second power. Right? But isn't that exactly the same as the height of that point? Yes? And if I say, hey, what's the derivative of e to the third power, or what's the derivative of e to the x at 3? You would say e to the third power. But that's actually how high it is. So the height of the function is equal to the slope of the tangent line at that point. That is the only function that does that. Only one of them exists. Only one function in all of the universe of functions behaves this way. And it is this function, e to the x. And so you ask why. It's actually the other way around. We needed a function that behaved this way. We discovered that e to the x was the only one that did it. So we actually had to come up with the base that made it happen. If I tweak that base, if I say instead of e to the x, if I use 2 to the x, then the derivative is not 2 to the x. So it's not, because the way this one curves, it's slightly different than e to the x, the pitch of the tangent line won't match the height. Only one function behaves that way. It's e to the x. You'll study that more in calculus too. You'll look at it even deeper and you'll see that, well, it's actually really nice, but that'll come later. Okay. So e to the x is the only function that is its own derivative. Now I should put a little asterisk on that. There is another function, all right, that is that way, all right? So, but I'm not lying to you. Look, it's that function. The derivative of that is what? Is 0. And so why do you think we don't use this one? It's the trivial function. It's the f of x equals 0 function. What does that function look like? A flat line, right? How boring is this, right? This is a very boring function. So what we say is that e to the x is the only non-trivial function that is its own derivative. This function is trivial. All right. So it is the function that is the only function that is its only derivative. And with that, you can blow the doors open on now taking derivatives of more complicated things. So like if we have something like, this is on your formula sheet, by the way, all your derivatives are listed out, right? And you have, that's on there, e to the x, derivatives e to the x. So if you have something like y equals e to the sine x, and you're asked to find the derivative, now you have to bring in all the things we know about derivatives. Is this power rule, product rule, quotient rule, chain rule? What is this? Is this a power? Is this a number? Is this a variable to a number? No, right? So how do you say this? Like if you were saying this is e of sine of x, right? E of sine of x. So this is actually composition, right? Chain rule. So this is where you have to look at the layers, and you're like, okay, I have the derivative of e to something. What's the derivative of e to anything? Itself, right? Itself. So I should write down e to the what? Sine x. But then chain rule says times the derivative of what was up there, which is cosine x. And that's it. That's your derivative. There's only one thing that's new here with this last 10 minutes I was showing you. Everyone needs to understand that the derivative of e to the x is itself. Here's another one. What about x squared e to the x? What would the derivative of that be? You have a product rule here? So I'm going to do derivative of this one, which is times e to the x plus derivative of e to the x, e to the x times x squared. And then you could clean things up. You could actually factor what out? X e to the x. And you'd be left with what, 2 plus x? You could just factor it. I'm just saying it could be cleaned. Now, we'll spend more time on this next class. I just wanted you to see at least to start. We're going to look at exponential functions. This is the very special one. And we're going to look at log functions. We'll probably knock that out in the first 20 minutes of class next time. Like, what's the derivative of exponential? What's the derivative of logs? And then we get to L'Hopital's rule, and that's the last topic for the test. So I know that it says on our schedule we're behind quite a bit, but the next 3 sections I'm going to knock out in the first 20 minutes because the 3.1 and 3.2 are a review from college algebra. And I'm not going to review exponential and logarithmic functions in here. All right. What are you doing for homework? You have a take-home quiz problem, right? Due at the beginning of class next time on my desk. And then you also have just the homework that's on the schedule for related rates. See how you do with that. And don't beat yourself up over if you're struggling, like I said, but that doesn't mean don't try. All right? Have a good day.